Hi, AP Calculus. This is Lesson 7, Pumping Fluids. This is another one of those integration topics that are context specific. In that sense, it's similar to fluid force from Lesson 74. I do not believe I have seen fluid force or pumping fluids on past AP exams. They could be asked if they give you very specific contextual questions, but they don't assume that you bring in knowledge of pumping fluids or fluid force into the AP exam, so they have to be very explicit in defining everything, giving you all the formulas. Okay, so that said, you probably won't see it. It's one of those classic contexts from calculus. So let's begin exploring the context. Work is equal to force times distance, where force is measured in newtons, distance is measured in meters, and the resulting work would be measured in newton meters, which we give the name joules. So, to move a weight of 1 newton vertically, a distance of 1 meter, require 1 joule of work. But to find the number of joules required to pump a fluid up out of a tank, we use a definite integral to sum the products of the weights of the thin sheets of fluid and the distances through which the sheets are to be moved. Look, if I have a rectangular tank, it's full of water, there'll be these sheets of water. I've given you a sheet right here. I think if I asked you, what do you think the height of the sheet of water is, you probably would tell me what? dy. Why dy? There's a little cut over here, that's a y1, another cut here, it's a y2, so that's a dy. Or we can ask what this little red line here is. It's going up vertically. Well, we call it the height, and that's the amount of distance that the sheet of water needs to clear for it to be removed from the tank if it's being pumped upward. So let's assume our tank is 6 meters tall. That's not just the water, it's the actual tank. And it's 10 meters long and 4 meters wide. The volume of the tank is 240 cubic meters. Now let's assume the tank is full of water. The water goes right up to the top. So there's 240 cubic meters of water in this tank. The question is, how much work does it take to pump all the water up out of the tank? First, let's consider the sheet of water. What's the volume of the sheet of water? Well, the volume of that sheet of water is going to be 4 times 10 times dy, or 40 dy. Now, if I wanted to calculate the weight of that sheet, do you remember this from lesson 74? You could use something called weight density of water, which was 9,800 newtons per meter cubed, and you can multiply it times the volume. So we have 9,800 for the weight density of water. We have 40 dy for the volume of the water. So the weight of that sheet of water is 392,000 dy. And of course that's measured in newtons. Now we only deal with is the height being the distance from the sheet of water to the top of the tank, because you're pushing that sheet vertically up out of the tank. So if we were to put this on a coordinate system, what do you think h would be? Let's say you put the origin right down here, right? So you put the origin right down here. Okay, what's the height, of the tank? What's the top of the tank? Top of the tank is 6 meters. So what is h then? H is going to be 6 minus y, right? 6 minus y. So our height is going to equal 6 minus y. So how much work is done on just a sheet, that one sheet of water, a sheet of water, to remove it vertically out of the tank? Well, how do you get work? It's force times distance, or 392,000 dy newtons times your height of 6 minus y. Okay, that is the work required to get a sheet out. So how would I get the work required to get all the sheets out of the tank, like all the water out of the tank? You just use a what? Use an integral. And is it going to be an integral in y dy or x dx? Y dy. You pump it out vertically. You already have y in your volume equation, in your work equation for a sheet of water. All right, so what's the total work then that's being done here on the water to get it out of the tank? Well, your total work for all the water in the tank to remove it completely is going to equal the definite integral from y equals something to y equals something. What's it going to be? From y equals 0 to y equals 6. There's a sheet of water all the way down there at 0, the sheet of water all the way up at 6. We have to calculate the work required to get each one of those sheets out. And then what do we say that the work for a particular sheet was? We have 392,000 6 minus y dy. That's what we had gotten, and I just arranged it so that the dy was at the end and it was a normal integral. Now you just use the first part of the fundamental theorem to evaluate this here, or this integral, which is no problem. And if you do that, you're going to get 7,056,000 joules. Good. And that, of course, is the total work required to remove all the sheets of water, to remove all the water vertically out of the tank, to pump the water vertically out of the tank. All right, let's look at another one of these problems. This time, instead of having a rectangular prism for a tank, we'll have one of these horse trough kind of situations, triangular prisms. We had to pump the water again vertically up out of the tank. And whereas in the last problem we had the tank completely full of water, this time we'll only have the water only setting up to a certain level when we start. All right, now problem, our tank is 20 meters long, and its cross sections are isosceles triangles with sides of length 5 meters, 5 meters, and 6 meters. The tank is filled with oil, this time oil, not water, to a depth of 2 meters. That's as high as the water goes. So we're supposed to find the work done in pumping the oil out of the top of the tank, and we know that the weight density of oil is 5,000 newtons per cubic meter. All right, so let's set our coordinate axes. Let's put them right here, and we'll solve for the work required to get half the volume of the tank pumped out, and then just double it. That'll probably be easiest. You could, of course, approach it other ways. All right, so the work to move out any sheet of water is going to be what again? It's going to be that weight density of oil, in this case 5,000 newtons per cubic meter, times H. H is what again? H is the distance a sheet of water needs to clear in order to get outside of the tank. And then you multiply that times the volume of the sheet of water. So our weight density is 5,000. Our height, well, it's going to be, height is going to be what? This distance right here between the sheet of water, whatever sheet you're looking at, and the top of the tank. And what does that seem to be? On our coordinate system, it'll be 4 minus y. H is equal to 4 minus y. I'd say, where'd you get that from? Well, look at our triangle, okay? This is 5, this is 6, all right? And this is isosceles triangle again. We're only looking at half the tank right now, so kind of keep your eyes on this triangle, this blackened out triangle. What do you notice about it? It's got an upper distance of 3, a hypotenuse distance of 5, so this must be a 3, 4, 5 triangle, right? So that was the height, is 4. And now the last thing, we just have to deal with the volume of the sheet. And you think it would be easier, but it's not quite as easy as before. Why? Because if you look at that sheet, the volume, kind of length times width times height, no problem. But you notice if you took a higher sheet versus a lower sheet, they'd actually have different widths. So it's got variable width on it. So you got to deal with that variable width. Anyway, so let's get the volume of a sheet. All right, well, you know it's gonna, the 20 part's not gonna change. That's the length, and the height isn't gonna change, it's gonna be dy. But the width, it's variable, right? It's variable. So how are you gonna calculate that? How are you gonna calculate that? It's really x equals 3/4 y, isn't it? Do you see it? I mean, if I asked you, what's the equation for this line right here, right? Assume that was a line. What would you say? You'd say the equation is y is equal to 4/3 x, wouldn't you? I mean, this is a 3, 4, 5 right triangle. It's got a height of 4. You're going over 3, so this is just rise or run. And then you want to convert that into x equals 3/4 y, because we're in y dy. Okay, so what's 20 times 3/4? That's like 5 times 3, which is 15. So you're talking about 15y dy. So what do we have? We have the work required to move one sheet of water vertically out of the tank. Now we have to deal with this issue of getting all the water out of the tank. So what's the work going to be? The work to remove all the water is going to be the definite integral from y equals something to y equals something. What will those y's be? We're going to go from 0 up to 2, because you're only going to look where the sheets of water currently are, and then we multiply it times this thing we have, 5,000 times 4 minus y times 15y dy. All right, so you integrate, and after you integrate, you're going to get 400,000 joules. 400,000 joules. But is this really all the water? No, this was all the water to get out of half the tank, right? Because I went ahead and looked at this slightly differently. So we have to double up our numbers. So truly the work here is going to be 800,000 joules. All right, you can do this. I know you can. It's good to learn all sorts of contexts for integrals, but don't expect the specific knowledge for this context or for the stuff in Lesson 74 to be required for you to know.